So lesson 0, I like to call it the fundamental problems of, and then I can't help myself, I like to call this applied linear algebra as opposed to abstract linear algebra, which is actually the origins of this field, historically speaking. Okay, and then somebody just said out loud what I like to call problem 0. It's the prerequisite problem to the class. Will you, somebody said that just now. Could you? Yeah. So use math to model and solve real-world problems. So this is just a review. And then I have a question for you. When we say math, what do we mean in this class? So when we're talking about linear algebra, very, very special type of math, what does it actually mean? Vectors, matrices, and then one of the things that we're going to talk more about is problems 1, 2a, 2b, 3, and 4. And in reality, at this point, we also have problem 5, 6, 7, and 8. We're not going to talk about, this is called, these problems in linear algebra, I call these personally advanced linear algebra. Problem 7, as written in your notes, I actually, in my PhD thesis, I was working on creating an algorithm to solve problem 7. It's open work. This stuff has not been done for all problems yet. There are still people that make lots of money from the National Science Foundation to create algorithms to solve these problems on computers. So, you know, it's unfair to say like, oh, all of this is done and all you have to do is translate. But the whole concept is, in this class, we're going to focus on using math. What does math mean? Vectors and matrices. And then also, once you have them in vectors and matrices, we're going to try to state problems 2b, 3, and 4. Okay, just as a review, what did we call this in student life? Yeah, and I don't mean, you know, I don't really care about being filthy rich in my life, and I think that if people cared less about that, we'd probably be better off. You might call this have a salary, right? I have to be a little careful when I say make money, because I can hear Gordon Gekko's greed is good. And that's not really what I'm talking about. I'm not talking about becoming filthy rich and like making money off the fact that labor unions are not strong like Amazon does, or, you know, making money by selling other people's data. I'm really talking about like having a good, healthy paycheck where you're paid to use your brain to solve math problems. Okay, what was problem 1? Okay, and matrix vector multiplication problem, we said let m and n be an element of of natural numbers, so these are dimensions, right? And then we said let A be a matrix. What size is the matrix? Mango times November. And let X be November by 1. And then both of these are, what did we call those? It's my favorite word to sin in this class, because given. And what does it mean, given? Somebody's paid some ridiculous amount of money and spent a lot of time getting those things, right? So when we said is then the matrix vector multiplication problem is to find what? Yeah, unknown and desired. Vector B. What size is the vector B? Yeah, Rm. If I don't write the by 1, it's implied. Such that what is true? A times X equals B. Okay? What size was A? M by N. What size was X? N by 1. What do we care around campus? The inner dimensions must agree. The inner dimensions must agree. So here, how many columns does A have? N columns. How many rows does X have? N rows. Those cancel out, and the outer dimensions store the size of the output. So what size is B? M by 1. So this is a output vector. Okay, so then we sing our favorite song. What's our favorite song? Yeah, so we're going to define f of x. So this is a very, very famous function. What's the function? A times x. And we're going to call this be the matrix vector multiplication function with what to be true? Where does it come from? Where does it go? Okay, it takes in vectors of size n, spits out vectors of size m. And then now we're actually really ready to say something intelligent here. Okay, what is the domain of f? Rn, and that's also equal to what? Why is it equal to the domain space? Why is this true? Where does that come from? Let me ask you this. What did we call this thing? Is it a relation or a function? What are the three properties of functions? That's special functions. That's very, very sexy functions. Right? What are the three properties of functions? That's property number 2, right? Every function is a relation, first and foremost, such that the domain is equal to the domain space. And then what's the third one? Any input element gets mapped to only one. It doesn't have to be unique. There could be the same output has multiple inputs, but for sure if you have one input, what's the maximum number of things that could be mapped with it? 1. What's the minimum? 1. No, the fact that the domain has to be equal to domain space immediately implies all the inputs have to be used, right? So this right here comes from lesson 2, set theoretic definition of a function. Okay. All right, and then what's the codomain? Yeah, so this is the size of the output. It's Rm with, what do we know about the range? Is the range guaranteed to be equal to the codomain in all functions? It's a subset. And what I might kind of just hint here is not necessarily equal. Sorry, April. I'll get there. Not necessarily equal, right? Okay. All right. What is the, so when we think about this, the MVMP, do you remember what we called that? Is a forward problem. Why is it a forward problem? Since we start with x element of the domain of f, which of course was Rn, aka start with input, and the solution to the MVMP is to do what? Yeah, evaluate the function f at this input to produce an output. Is to find output B element of, let me ask you this. If for sure I know that B is equal to A times X for some X in the domain, what do you know immediately about where B is? Yeah, it must be in the range. Why should it be in the range? What is the range? From lesson 2. I'm not asking you information about matrix vector multiplication because we haven't talked about it yet. I'm asking you information about the set theoretic definition of functions. What's the set theoretic definition of functions? The range is a subset of a codomain. But what was the range? Think about the set notation for the range?
That there's a it's in the codomain, and it also has a element in the domain that's linked to it.
Yep. The range is all things that are used in the codomain. So all vectors, in this case b, such that there exists an x, such that f of x is equal to b, or the ordered pair x comma b is in the relation. So by definition, the moment that I say that x is used to produce b under the map f, what do I immediately know about b? Do you have to know anything about matrix multiplication to answer that problem?
No.
Where's it come from? Set theoretic definition of functions. Now, the real question is, hey Jeff, are you sure that this is a function? Well, we haven't gotten there yet, right? Okay. Okay, so the whole idea in this problem is that we start with an input, we produce an output. Okay, what about what's problem 2a? Yeah, so non-singular linear systems problem. How did we abbreviate that for shorthand? Yeah, so we call that NLSP. All right. So in this case, what's one of the major difference between the non-singular linear systems problem and the matrix vector multiplication problem? Oh, yeah. So, okay, so what are the things that we need for the non-singular linear systems problem? Okay, so we need and b. Yeah, so why don't we call that an output vector? When we use the verb or the adjective output, what do we mean? Output from the matrix vector multiplication function, right? So it's an output from that function. What else? What's another major difference? In the matrix vector multiplication problem, what size was the matrix? Mango by November, so it could be general rectangular. In non-singular linear systems problem, it's a square, and not only is it square, but it's also non-singular, whatever the hell that means, right? We don't know what that means yet, but my claim is we're gonna learn that, and I kind of want you to understand that non-singular is special. Okay, so we're given a square matrix that's non-singular. What else are we given? Output vector. The moment you know that the output vector is from the matrix vector multiplication problem, what size must it be? Must be n by 1. Then the NLSP is to find what? Yeah, unknown and desired input vector. What's that input vector going to be called? X. What size would X be? N by 1, such that what is true? Equal B. Okay, let's go ahead and just check real quick. What size was A? Yeah, you've got to be a little careful. We won't say it's n squared because n squared compresses too much information. Remember that when we have that little dimensions, we'll talk more about this later in the course, that little x means the thing before x is the number of rows, the thing after x is the number of columns. So the x is literally a times, right? So n by n, how big is the vector x? N by 1. What do we carry around campus? Inner dimensions must agree. Is the number of columns of A equal the number of rows of X? Check. Those cancel out, and we're left with n by 1, which is the desired dimensions that we were started with. The one extra condition on A was what? Non-singular. We will learn. I don't want you to worry about this right now, but what I'm trying to do is close the loop and really have you focus on the, review why we spent time on this. So this is a note. We will see that non-singular matrices are very special. Perhaps we might say they are what applied linear algebraists dream about. I might say fantasize about, except you actually recognize these fantasies, so it's not like pie in the sky. It's like they exist in life, right? Fantasy is like one of those things you may never get. Dream is something you might get in a few years, right? Yeah, okay, applied linear algebra, dream about. They're gorgeous. They are very beautiful. What's that?
Are they restricted?
Depends on what you mean restrictive.
I don't know enough.
Okay, so we'll get there. So one of the things, so in particular, with a non-singular linear systems, do you know one of the first things we say? The range of f is equal to the codomain of f. So in particular, these, like this goes back to what my friend Sam was saying earlier. This is what we call a bijective map for those of you that have taken, we're going to get here, don't worry about it right now, I'm just kind of setting things up to understand what the differences between the different problems are. What does bijective mean for those of you who've taken set theory? Yeah. You remember that being one of the most beautiful things that you could get in function theory? There's, for everything in the range, there's only one pre-image, and everything in the range is for sure hit. Right? So it's the best a person can get. Okay. All right, so here we go. We're talking about, what are we doing right now? So we had problem 0, which was real world problem. Where does problem 0 show up in these two problem statements? And it's quoted right there. It's in quotations on that board. The word given. Problem 0 is the word given. Right? Without problem 0, you couldn't have the word given. If you have problem 0, we actually construct those matrices. And we're going to do that in class. That's part of that whole thing, right? Okay. Problem 1, what was problem 1? The forward problem of matrix vector multiplication. I start with a matrix and an input vector. I produce an output vector. What do you know about the matrix in problem 1? M by n. Is it non-singular? Is it special in any way? Only rectangular, m rows, n columns. Okay, what's problem 2a? Yeah, so literally problem 2a is a special case of the backward problem of problem 1. Right, so there's a whole subclass of problems in problem 1, which is to work with non-singular linear systems and to map forward. Problem 2a is to take that subclass and then map backwards.